One of our first tasks was to essentially compare the finite difference method with the DVR approach in an effort to see which one produces more accurate results. And then, of course, to cross-check that with the exact solutions given to us by the equation that can give us the wave function that incorporates the Hermite polynomials. So we start with programming the finite difference method here, and the formalism for that is essentially given, sort of a discretized version of the formula that we have above, and how that would look like in the matrix. And since we're considering less points, namely only 3, we expect slightly inferior results compared to the DVR, since the DVR takes more points into account. We have a modularized function for the normalization process, so we can call on this on any particular wave function, and that'll essentially give us the normalized wave function before the plotting logic occurs. We've defined our potential, our boundary points, and a position space. We've chosen to essentially produce the kinetic energy matrix and the potential energy matrix that the Hamiltonian consists of as 2 separate matrices, although there is an option to essentially do that in one shot. Since we have to add them, we can essentially incorporate that logic here and save ourselves some work. We produce finite values for, we essentially produce values for the energy eigenvalues for a particular value then. So we grab the first 10 and we can see that we do have results for that. And if we go through the normalization process through the normalization wave function, we can essentially plot the normalized versions that the finite difference produces. And then if we do that with the DVR approach with a minor change of redefining the kinetic energy matrix such that it satisfies sort of these constraints here, we essentially arrive at energy eigenvalues as well if we grab the first 10. And essentially comparing them gives us an idea that the DVR method essentially gives us more precise values for the energy eigenvalues. And the graph is more or less consistent, but we do see better precision with the DVR approach. Of course, here we introduce the Hermite polynomials approach. This was an equation taken from our overleaf document that can give us the sort of more of an exact perspective. And assuming that this is without dimension, we take m and h bar and omega and so forth to be 1. And this is essentially what we produce. We have our harmonic oscillator wave function. We choose to incorporate the normalization constant here instead of letting the normalization function produce the constant itself. This gives us more of an accurate view. So we don't actually have to take the result of the harmonic oscillator wave function and pass it through the normalization logic, because we do have that normalization constant. And of course, the exact solution gives us graphical results that are more or less aligned with what we have across both the finite and DVR approach. As for the comparisons, we can compare the finite difference, the DVR, and the Hermite polynomial approach. And we do see an overlap between each of these, each of the wave functions produced by each of these approaches for a particular collection of n. And we can also check the square of those wave functions for the probability density, although if these are consistent, then we would expect them to be consistent for the square as well, in which case they are. But of course, for higher values of n, we do see deviations occur, and this isn't really the case. If we choose, let's say n equals to 7, we'll see that deviation doesn't exist to that extent. Although if we ramp this up a bit, we do see that deviation occurs. Although that can be solved by expanding our bounds here. So instead of choosing, let's say, -6 to 6, if our lower and upper limit is -10 to 10, then even if we access a value of n that is equal to 18, we still have accurate results. And so we'll move on here. Although we do see some discrepancies in the graph, this sometimes happens when I increase the bounds. Some of the graphs become inverted. Although this isn't too much of a problem, we can add a negative to some components of the plotting logic, and that'll fix that. But they're still accurate. Now we can sort of look at kind of what happens with our boundary conditions to see if that's consistent as well. We have the DVR approach here, and of course we could extend this to the finite difference method by redefining the kinetic matrix. But what we do see is that, if we plot a number of wave functions, namely 15 in this case, that are wave functions that are produced with the DVR method, we do see that they that at the boundaries they are in fact 0, and this is because we've remained consistent with this idea of having psi of 0 as 0 and psi of n as 0, and so we've essentially forced our boundary conditions on the DVR method here. Now the Hermite polynomial approach doesn't really abide by this for within this particular range. We see that property doesn't hold here, although it will if we expand our range, right? If we look at a particular wave function, we do see that it's true, but at large it might not be in this case, because it might be more apparent if we extend the bounds here. Although I will say that if we continue to access, let's say if I set I equal to 8 here, we do see some deviation occur at these endpoints, and this is proportional here. I mean, it just keeps kind of becoming a bit bit wild here. But of course, if even for let's say if we were to take n equals to 15, if we expand our range, all of these problems seem to go away. So if we go from -10 to 10 in this case, and if we run virtually every cell again, we do see that the wave functions are a bit more compressed here. We're sort of looking at them from from a broader scale, but we do see that that now we're kind of on the same page with what the DVR does, and we do have better, more precise results for converging at the endpoints. Now, there's also an additional concern here towards the bottom, right, where we had discrepancies, and that you can see that discrepancy doesn't exist. And again, we do have some graphical inversions, which shouldn't be too hard to deal with. There was an additional objective to look at the square root of the sum of the square of the differences. So really the root mean square error without really the mean. And that logic is pretty much here. So we're not dividing by anything because we're foregoing observing what the mean is and so forth. But the value of I in this case corresponds to the value of n. And then what we have here is, let's see, let me go ahead and change back to 6. So I mean, as we go out, we do see discrepancies, obviously, but on a smaller window, we have these results where the difference or the discrepancy, really a measure of the difference between the DVR and the exact is very it's very close to 0, and we've graphed them. I think this was part of the earlier version of the code, but nonetheless, this does address calculating the sum of the square of the differences between the DVR and the Hermite. And this observation that we made here is true even if we look at the finite difference method, where we have virtually what we had with the DVR. And we've also looked at the square root of the sum of the square differences. And we can sort of do a side-by-side comparison of these numbers, right? So, this correlates to, let's see here. So this is the finite and this is the DVR here. Now these numbers are different, but just a little bit more further out here. But nonetheless, they both are, very, very close to zero. We're going to now sort of look at the Fourier transformation and the inverse and calculating the derivatives and so forth. So looking at this from the lens of the DVR approach, so the wave functions that we produce to make our observation here will be borrowed from the way in which the DVR produces them, and the formalism that relates to that. We have essentially the same code here that helps us do that. And of course, we have our Hermite implementation. That way, we can sort of compare and so forth. Now, coming into the Fourier transformation, I think it's useful to recognize that the Fourier transformation, if we have a wave function that's represented in, let's say, in terms of time, the Fourier transformation can represent that, in terms of something else. So sort of another representation, right? In this case, we have a sinusoidal wave, a cosine, and if we choose to represent that in terms of frequency after that Fourier transformation takes place, we see that the frequency is more or less consistent here. There's only one frequency, and so we see one spike, and we can expand this idea or extend this idea into, if let's say we had a wave function represented in position space, or a position representation, then after that Fourier transformation takes place, we could attain sort of the momentum representation. So that was a critical observation to make here on my end, at least. And as far as the formalism is concerned, there was an article here that sort of this article sort of outlines what the discretized version of that would be, so that it would be sort of easy to sort of program. And we've essentially just translated that into code here. So we can see the whatever's in the exponential, let's say, is contained within np dot exponential, and then we have that argument contained here. And then of course we multiply by delta x, and f of x sub m is essentially here, where we go to a particular column denoted by I, and we can access an element within that column denoted by m. Now, what's interesting to see is that if we look at the ground state wave function, namely this one here, then if we're looking at the derivative for the ground state wave function, using this paradigm of the Fourier transformation, or not the derivative really, but just looking at the Fourier transformation itself, we see that we kind of have a spike here at 0, and that more or less correlates with what we see for the ground state wave function. And we can extend this observation into the into n equals 1, and n equals 2, and so forth. And I'll actually have to run all the particular cells at once in order to do that, because it has to sort of remember what the variables are across these particular cells. But just sort of toggling this helps us get a better visual depiction for we can sort of compare, much in the same way we were doing before with the picture on Google. We can sort of compare that these spikes with what we see in the Fourier transformation after the Fourier transformation takes place. So this is sort of a verification that it is in fact working. Now, if we look at the inverse Fourier transformation, it's defined as such. The article made that clear. And if we take the derivative of both sides, then we can essentially arrive at the first order derivative, using the inverse transformation. So, when we take that derivative, we'll essentially have an extra constant attached at the end, which is essentially why we see this snippet of code much longer than the first. And if we essentially graph the derivative of, let's say, n equals to 0, right? So this is the graph for the ground state wave function within this paradigm of the inverse Fourier transformation and calculating the derivative and so forth. We see that it correlates with n equals to 1. So if I were to graph the derivative of n equals to if I were to graph the derivative of n equals to let's see here. If I were to graph the derivative of n equals 0, my resultant graph should more or less look like what we have for n equals to 1. So for n equals to x, if we look at the derivative of that graphically, we should generally expect a shape that looks like the graph for n equals to x plus 1, if we're looking at the first order derivative. Of course, if we're looking at the second order derivative, then it would be n equals to x plus 2, as far as the graphical comparison is concerned. Now, it seems like this idea works for the ground state wave function, but it doesn't seem to work. It doesn't really seem to work for anything beyond the ground state. So this observation that was made, where if I graph n equals to x, then the derivative of n equals to x, that wave function in particular, should correlate to n equals to x plus 1, which we had up here. But that doesn't seem to work for let's say if I choose n equals to 2. I would expect or let's say if I choose n equals to 1 here, I should expect a graph that let's see. So this one I think is giving me the this is the ground state, and this is n equals to 1. And so this actually doesn't work, right? We don't in fact get the graph n equals to 2, right? So there's definitely some issue in the way that maybe the inverse Fourier transformation is programmed, although it maybe in some constant or so forth that I kind of have to track down. But we would expect for n equals to 1, we would expect the graph to be n equals to 2, and we don't actually see that here, and that's true even if we extend that for n equals to 2. But for now, just moving on a bit, the second order derivative for the inverse Fourier transformation, if I take what we had, if I take the code for what we had when we were programming the first order, we know that if we take the derivative again, we would essentially just have one more of what we have here, right? So we'll multiply by that again, although you could save yourself time by just putting that in a just squaring it using np dot square or something of that type. But nonetheless, we do arrive at the second order derivative, and for the ground state, again, this is consistent, right? So before I said for the first order, if we graph the derivative, we for n equals to x, we'll get a shape that replicates n equals to 1. But for the second order, for looking at n equals to 0 for the ground state, we should be expecting a graph that more or less gives us n equals to 2. So we're going by 2 now. And again, this is consistent, right? We do see that if we look at the second order derivative, and if we're looking at the ground state, we want this graph n equals to 2, and again that matches up. But if I look at n equals to 3, for instance, suddenly, or n equals to 1, we expect n equals to 3. Now that doesn't seem to add up. the graph for n equals to 3 is slightly more different than what we found down there. So there's definitely, some subtlety here that's going on that I'm not quite able to track down. But there is definitely, we do have results to some extent that can help us move forward a bit. Looking at the finite difference method for derivatives applied on the DVR wave functions, this is how that was defined on the board. There are some edge cases here. In our logic, we do j+1. We don't want to really do that at the boundary points. And so this idea of j+1 is absent from those edge cases. Again, if we do the second order derivative for the ground state, n equals to 0, we should expect n equals to 1. Let's see here. So it might be that it's inverted, but there's definitely some issue graphically going on here that needs to be sorted out. But that has been the progress, more or less.